Hey, I'm Kelvin. I'm a researcher at Waabi, and in the previous session on simulation, Siva walked us through sort of the various components necessary to build a high fidelity closed loop simulator for self-driving, right? So we saw how to build a digital twin of the real world, how to simulate high fidelity sensor data within that digital twin, and how to model the vehicle platform itself, right? So in this session, we're going to discuss how to generate and simulate the scenarios that populate the contents of those simulations. And before we get started, what exactly are scenarios and what kind of scenarios do we actually want for our closed loop simulator? So scenarios kind of form the content of the simulation. They specify what kind of actors are in the scene, where they are located, and how they behave over time. And they're essentially the simulation counterparts to the kind of traffic scenarios we might encounter in the real world. Only now we're going to simulate them in a high fidelity closed loop simulator instead. So if we were to allude back to sort of our old video game analogy, scenarios are almost kind of like the levels of a video game that we can use to test and train a self-driving car with. Okay, so let's go through a quick example of what a scenario would look like in a little bit more details. So to create a scenario, first, we'll need to specify the environment around the self-driving vehicle. So for example, where is the self-driving vehicle located, right? What does the road topology look like around the self-driving vehicle? What is the weather condition like, et cetera, right? Next, we'll also want to specify the initial conditions of the simulation. So here, we'll specify what actors are in the scene, right? How they look like, what are their initial dynamic states, et cetera. So for example, here we specified a scenario with roughly maybe 20 actors in the scene, some of which are cars, some of which are sort of like larger trucks or buses, right? And they're all moving, or yeah, they all have like highway speeds initialized. And then finally, we'll want to specify how these actors will behave over time and how they might react or interact with the self-driving vehicle. So for example, maybe we want to test the self-driving vehicle's reaction to cut-ins, right? So we'll want to specify that the actor to the right of the self-driving vehicle will cut in front of the SDV with a certain definition of severity or aggressiveness, right? Okay, so another basic question we should answer is, what kind of scenarios do we want for training and testing a self-driving vehicle? So the most basic kind of scenarios are nominal traffic scenarios, right? These are the kind of typical traffic scenarios you encounter when you drive in public roads on the highway or in city streets. And these nominal scenarios can be used to train and test a self-driving vehicle under conditions that we'd expect to normally encounter when we deploy to public roads. Now, as Siva mentioned in the previous session, self-driving vehicles also undergo a lot of structured testing in the real world. And this allows us to test the self-driving vehicle in sort of potentially rare situations in a very controlled and repeatable manner. So for example, as we discussed, to test the SDV on how it might respond to various cut-ins at various levels of severity. So like in the real world, we can recreate these structured test scenarios for simulation as well. But unlike in the real world, we can now run these tests much more safely, much more scalably, right, at a much larger scale, and in a much more controlled and repeatable manner to really precisely characterize the performance of a new autonomy stack before we deploy it to the real world. So here we're just showing an example of where we were able to parameterize the scenario and maybe intelligently sample different points in the parameter space of the scenario to really characterize where the self-driving vehicle performs well and performs maybe a little bit more poorly in that parameter space. And we'll go into this in a little bit more detail later as well. And then beyond structured testing, it's also really important to be able to verify how the SDV would behave in rare but safety critical scenarios. So for example, how the self-driving vehicle might behave if this actor in orange here sort of like speeds up quite a bit on like 2 lanes away and then it just aggressively cuts in front of the self-driving vehicle. So this allows us to discover potential issues with the autonomy stack early using simulation and also verify the safety of the self-driving vehicle before it ever gets deployed to the real world. And additionally, these scenarios can also be used to more effectively train the autonomy stack in simulation, as opposed to, say, using just nominal traffic scenarios that we've collected from the real world, which could be usually quite boring. And then finally, it would also be very useful if we had the ability to also take any log that we've captured from the real world and then just turn those into reactive closed loop simulations, right? And then we can resimulate those scenarios and generate tons of variations of those scenarios as well to really like test and train the self-driving vehicle with. So this will allow us to test different autonomy systems under the same conditions and answer counterfactual questions like, what would have happened if the SCB had braked earlier? Or what would have happened if an actor in front of us hard braked instead of going straight, right? Cool. Yeah, so hopefully through this discussion, I've convinced you that there's sort of a vast variety of different kinds of scenarios that we'd like to test and train a self-driving vehicle with, right? And an ideal simulator should be able to generate and simulate all of these scenarios and many more. So this is the topic of today's session. Sort of in the first half of this talk, we'll discuss various approaches to scenario generation that have been proposed in the literature. And after that, I'll give a brief introduction into actor simulation. So how can we sort of model the behavior of other traffic participants in a scenario, and then use these models to sort of simulate the various kinds of different scenarios that we just discussed earlier. So let's get started with scenario creation. So in general, there are four main approaches to scenario generation: manual creation, procedural generation, extracting them from real world logs, and generative models. Each of these approaches have their own pros and cons, which make them suitable for different applications. And as we'll see, these different approaches to scenario generation are also not mutually exclusive, but actually complement each other to support various kinds of scenarios that we want to create. So manual specification is perhaps the most straightforward approach. This approach involves having a human manually specify various aspects of the scenario, either through a domain-specific language like OpenScenario 2.0 or CNIC, or through graphical user interfaces, where maybe one can drag and drop actors onto a scene, configure their characteristics, and specify how we'd like them to behave, right? So the advantage of this approach is that it gives the human author very precise control over the entire scenario. So for example, if I wanted to brake test the self-driving vehicle, I can really precisely place an actor at various distance ahead of the self-driving vehicle, and then configure those actors to brake at various levels of severity. And this approach allows us to really precisely also recreate safety critical scenarios from public databases, for example, and then evaluate how the self-driving vehicle would behave in those scenarios. However, as you can probably tell, creating scenarios in this way, it can be quite challenging because specifying all of these scenarios in this way can be quite tedious, right? So this would really limit the scale and diversity of the scenarios we can create in this approach. So an alternative is procedural generation. So here we can compose predefined rules, heuristics, and parameters into almost kind of like recipes for how to generate scenarios at scale. And this has been shown to, or successfully applied to generating realistic scene layouts, or even realistic maps from scratch. For example, in an open source simulator called MetaDrive, they use procedural generation to sort of create really realistic maps for training and testing a self-driving vehicle in. Now, this approach allows us to generate a lot of variations at scale, but at the same time, we can also encode constraints on the kind of scenarios that we want to generate and what constitutes useful or realistic scenarios within those heuristics and parameters themselves, right? However, designing good rules and heuristics can be challenging and time-consuming, and it requires a lot of human expertise. And at the same time, the use of these rules and heuristics limit the realism and diversity of the scenarios we can generate in this way. Cool. Instead of creating scenarios from scratch, we can also extract scenarios from logs that we've captured from the real world. And this is what many popular planning simulators do today. For example, NuPlan, Nocturne, and Waymax. And in addition, we can also generate variations of those scenarios by fuzzing the parameters of the scenarios or modifying the behaviors of the actors in the scenario from the original log. The advantage of this approach is that it yields realistic scenarios by definition, and it also allows us to leverage the scale and diversity of real-world data. However, we are still limited to what we can see and collect in the real world, and this can be problematic because everyday driving, especially on the highways, is usually pretty uninteresting for training and testing purposes, right? And we'll also seldom come across safety critical scenarios, but these are sort of precisely the kind of scenarios that we do want to upsample in simulation. And then recently, several papers have studied how we can actually automatically generate realistic scenarios at scale through the use of generative models. So for example, SceneGen here learns an autoregressive model that iteratively inserts actors into the scene. SimNet is another approach that learns a generative adversarial network that predicts a rasterized image of the scene. And then from this rasterized image, you can then extract like a vector-based representation of where the actors are. And then there's been two recent open source simulators called Sledge and Torch Drive End, which make use of diffusion models and normalizing flows respectively in order to generate scenarios from scratch. So the advantage of these approaches is that they're fully data-driven, right? And so the realism and diversity of these scenarios just improves with more data. And at the same time, we no longer rely on handcrafted rules or heuristics, which are not only challenging to develop, but they also limit the scale or diversity and realism of our scenarios. However, the methods presented so far generally have limited controllability, which limits its applicability in use cases where you would want a little bit more precision over the kinds of scenarios you want to generate. For example, if you wanted to generate a ton of structured testing scenarios, right? And in addition, most of the papers we've considered so far generate only the layout of the actors in the scene. But as we've seen, we'd also like to generate other aspects of the scenario, like what is the weather condition? How do we want the other actors to behave, right? What is the goal of the self-driving vehicle or the destination that it wants to reach? So to address this issue of controllability, several recent works have proposed ways to imbue these generative models with more controllability, right? So for example, this first work on the right or left for you guys is scene control, which learns a diffusion model of traffic scenes, and then it uses guidance functions to perturb the sampling process towards samples with high realism and high constraint satisfaction. This allows us to encode or use high-level constraints in order to specify things like how many actors do we want in this scenario, how dense should it be, where should the actors generally be placed, how large and fast they are, or etc. Another approach is RealGen, which first retrieves a set of template scenarios from some external database of real-world scenarios, and then generates novel scenarios that are similar to the template scenarios. More recently, some papers have also taken controllability one step further so that we can control the kinds of scenarios we want to generate through natural language directly, right? So for example, LCT-Gen uses a large language model to generate a structured description of a scenario, and then it uses a generative model that to generate the scenarios themselves, conditional on that structured description. So these are all super exciting directions to improve the controllability of generative models for scenario generation. Yeah. Cool. And now we've discussed various ways to generate scenarios, whether it's through manual specification or using generative models directly. And to ensure that we've adequately tested the self-driving vehicle, we also need to make sure that the scenarios that we generate actually cover what the self-driving vehicle might observe in the real world, right? So in other words, the real world is extremely diverse and complex. And to safely deploy the self-driving vehicle to the real world, we need to ensure that testing covers all the possible scenarios that might occur and characterize the SDV's performance across those scenarios. So therefore, we need a way to generate scenarios that will help us maximize test coverage. And this is challenging because the world is really vast, right, and very long-tailed. And it can be infeasible to test the SDV in sort of the infinite number of configurations of scenarios that can exist. So this motivates the need for a more efficient or intelligent algorithm to help us maximize coverage efficiently and characterize the performance of the SDB efficiently. So there's been a couple papers recently that come out to explore this idea of using intelligent sampling in order to generate scenarios that maximize test coverage. So for example, I'm going to cover this paper called GUARD, which proposes the following pipeline. First, we're going to test the SDB on some random initial scenario, and then we're going to update our estimate of the SDB's performance. So the scenario is shown on your right, and then our estimate of the SDB's performance is shown on your left here. Next, we're going to generate a new scenario and test the SDB on that new scenario. And importantly, the way we test or generate the scenario is we want to find a scenario that maximizes our information gain about how the SDB would perform. Cool. And then finally, we're going to iteratively repeat this process by generating new scenarios and testing the SDB in new scenarios to both improve our estimate of its performance and to maximize coverage. So importantly, the algorithm here will prioritize scenarios where we are most uncertain about the SDB's performance. So for example, where the decision boundary lies between when the SDB will pass or when it might fail. Cool. And that's it for scenario creation. Next, I'm going to talk about how can we actually simulate the behaviors of the actors in the scenario. And before we get started, what exactly is actor simulation? So at a high level, we're given a high definition map of the environment, and we're also given the initial states of the scenario, like what we specified earlier. And then what we want to do is simulate the behaviors of the actors in that simulation. So where they will go over time, how they will react to changes in the environment, and how their internal dynamic states might change as well. So we want to do this for every kind of traffic agent that we might see out there in the real world, right? And broadly speaking, we can categorize this into actors with rigid actors like vehicles, motorcyclists, etc., and deformable actors like pedestrians. So in today's session, we're going to primarily focus on how we can simulate the behavior of rigid actors. But note that there's also a vast literature on how we can simulate the behaviors of other actors as well, for example, pedestrians, that we will unfortunately not have time to get into. So now you might be thinking, how does actor simulation differ from other tasks in self-driving? So for example, in motion planning, we also care about learning to drive in the real world. And can we simply use SDB's motion planner to simulate actor behaviors? Well, not quite. In motion planning, our goal is to learn optimal driving behavior. That is, driving behaviors that are safe, efficient, comfortable, and follows traffic rules. And if we use an SDB's motion planner for actor simulation, we'll only train against and test against optimal drivers in simulation. But we know that human drivers in the real world are far from optimal. Human drivers can be frustratingly cautious or recklessly aggressive. And oftentimes their behaviors are irrational, right? And most notably, human drivers rarely abide by any traffic rules at all, right? So in actor simulation, we want to be able to capture the full distribution of human driving behaviors. And this will allow us to expose the self-driving vehicle to the diversity of possible scenarios it might encounter in the real world. And what about motion forecasting? Here, we're also interested in predicting the full distribution of human driving behaviors that we encounter in the real world. Well, there are three key distinctions between motion forecasting and actor simulation. First, in motion forecasting, because it runs as a part of the autonomy stack, it operates on partial and noisy observations coming from sensor data. In contrast, actor simulation, we're given perfect state information from the simulator, right? We also do not know the goals and intentions behind each traffic agent in motion forecasting, but oftentimes the goals and intentions of each actor is known to us and given to us because that's exactly what we want to control. And then perhaps most importantly, motion forecasting is an open loop task. The predictions of the motion forecasting model doesn't directly influence its future inputs. In contrast, actor simulation is a closed loop task where the predictions of the actor simulation model directly influences the future inputs it sees. So any small mispredictions by this model can then compound over time. And as we'll see, What this means is that a simple supervised learning setup is often insufficient to learn good actor simulation models. Okay, so perhaps the simplest way to get started in actor simulation is to just use rules-based behaviors, like the classic IDM model, right? So here we'll leverage classical car following models like IDM or lane change models like mobile to simulate actor behaviors. And this is actually what's often done in a lot of popular planning simulators like Waymax or Sledge, right? This is a very conceptually simple approach that's really easy to implement. And oftentimes it can give us pretty reasonable results as well, because we can enforce constraints like actors shouldn't collide with each other, or their actors shouldn't violate traffic rules, right? But this approach can only really take us so far. The problem with these rules-based approaches is that the rules we use are often far too rigid to simulate realistic human behaviors. So this might be okay if we're just trying to simulate simple lane following behaviors, but we often want to capture the long tail of actor behaviors as well, like complex non-compliant behaviors like cutting corners or illegal U-turns. We want to be able to simulate different kinds of driving styles, from cautious to aggressive drivers. And we want to be able to simulate realistic interactions between human drivers, like signaling, right? And simplistic models like IDM just don't allow us to do this. So what exactly do we want from actor simulation? Well, we want our actors to be realistic so that our simulations have low domain gap to the real world. We want them to be diverse so that we can make the self-driving car experience the full diversity of real world driving. And we want them to be controllable so that we can simulate scenarios with specific semantics. And this is really important for upsampling rare long tail scenarios for training and testing the SCB. So it's unscalable for us to handcraft rules in order to simulate all of these behaviors and hit all of these requirements. And a much better solution is to try to learn to simulate these actor behaviors from data directly. So we're going to start by talking about techniques to achieve each of these requirements, starting with realism. So behavior cloning is one approach to this problem. And the high-level idea behind behavior cloning is we're going to first collect an offline data set of state action pairs from human driving demonstrations. And then we're going to use this supervised learning, or we're going to use supervised learning to train a policy that predicts an action's one-step action given its current state. Now, this approach is appealing because it uses a very simple supervised learning setup that we're all familiar with. And we can also readily collect offline data sets for this purpose, simply by just observing how humans drive in the real world, right? This makes it really easy to scale the performance of this method with more data. However, policies trained in this way are well known to suffer from covariate shift, which means that the policies are not robust to out-of-distribution states induced by its own mistakes. So when we unroll these policies in closed-loop simulation, their errors compound, leading to increasingly unrealistic behaviors. So this is a fundamental problem of behavior cloning. And next, we'll take a look at a couple techniques to address this issue. One approach is to simply regularize the policy to avoid getting into these out-of-distribution states altogether. So for example, we can design losses that encourage the policy to respect traffic rules and avoid out-of-distribution states like collisions or off-road driving. We can also regularize the policy to stay close to observation states. For example, by learning a probabilistic forward model and then penalizing the policy for taking actions that lead it to states where the forward model was uncertain. So this approach is simple and it minimally changes the behavior cloning setup. And it also allows us to incorporate common sense knowledge about human driving behaviors into the learning process. However, it can be challenging to handcraft good auxiliary losses for this approach. And doing this poorly may add bias to the learning process. For example, by penalizing long tail behaviors that you actually want to capture. And another approach is to use data augmentation to make the policy more robust to out-of-distribution states. So for example, a clever way is to generate synthetic scenarios by perturbing the actor's trajectory and have it learn to recover from those perturbed states. Another way is to simply perturb the input data with random translations and rotations, right? And again, this approach is simple and minimally changes the behavior cloning setup. However, as with auxiliary losses, we still need to handcraft good data augmentation strategies so that we can expose the policy to out of distribution states that we expect the policy will actually encounter in closed loop simulation. So another solution or a more natural solution to this is to directly train the policy on states it will encounter during closed loop simulation. So to do this, a couple of recent papers propose to unroll the policy through closed loop differentiable simulation, feeding into the policy the states that it predicted or its predicted actions will induce. Then we can simply apply the same behavior cloning loss to minimize the difference between the policy trajectory and the expert trajectory. And this approach directly trains the policy to recover from its own mistakes. That is the other distribution states it will encounter when it gets unrolled in simulation. However, since we don't know how humans would actually, what the humans will actually do in those out of distribution states, we train the policy to only match the original human trajectory only. And this gives us a biased training objective that might ultimately impact realism and diversity. So what if we can query a human for what to do in these out of distribution states? This is the classical approach of the Dagger algorithm, where we iterate between training a new policy on behavior cloning and collecting a new dataset by enrolling the policy and querying an expert, interactive expert for action labels. So this approach allows us to supervise a policy with expert actions, even in out of distribution states. However, interactive experts are rarely available. And even when they are, they can be prohibitively expensive to include within the training loop. Finally, instead of querying an interactive expert for action labels, we can also encode a prior knowledge about what constitutes realistic driving into sparse reward functions. And then we can augment the behavior cloning objective with a reinforcement learning objective to supervise a policy in other distribution states. The behavior cloning component allows us to efficiently learn realistic human driving behavior from in-distribution states, whereas the reinforcement learning component allows us to improve robustness to out-of-distribution states. However, this requires us to manually design reward functions and manually trade off between the RL and BC objectives. And if we were to take this idea one step further, instead of manually designing the reward function, we can also learn the reward function from data directly. So one particularly common or popular instantiation of this idea is generative adversarial imitation learning, or GAIL. So here the idea is to learn a discriminator to distinguish between the expert's actions and the actions predicted by the learner policy. And then this discriminator can then be used as a sort of realism award to train the learner policy in closed loop simulation. Conceptually, this idea is really nice, really beautiful. It allows us to train realistic driving policies through closed loop training. However, training such a model is notoriously difficult in practice because of its minimax optimization objective. Okay, so the techniques we've seen so far focused on how do we learn realistic and reactive actor behaviors for simulation. And another critically important aspect is how to capture the full diversity of human behaviors possible in the real world. So let's take a look at some basic approaches to do this next. So one popular approach is to learn hierarchical policies to simulate actor behaviors. So this approach builds on the intuition that human driving is intentional. So by explicitly disentangling the high-level goals of the behavior from its low-level controls, we can potentially learn policies that better cover the main sources of multimodality in human driving. So for example, we can learn policies that model a latent variable indicating the goal of the driver, or we can learn more explicit hierarchies using waypoint goals or route goals to model the most salient sources of diversity in human driving. And this approach allows us to generate diverse multimodal simulations of how a scenario would evolve over time. However, trying to learn this hierarchy in an unsupervised fashion often leads to uninterpretable or entangled latent spaces. And explicitly designing explicit hierarchies can be difficult to get right. So beyond explicit hierarchies, we can also just try to learn generative models to capture multimodal distributions of human driving behaviors. And there's many ways we can do this, whether it's variational autoencoders, as we just seen before, or using diffusion models, as in recent works like CTG and motion diffuser, or using autoregressive models over discrete tokens, as in motion LM and Trajaglish. So we've covered this in a little bit more detail in the prediction session of this talk. So I will just leave it at this for now. And then finally, another popular approach within the community is to train a zoo of RL agents through self-play. So here the idea is to iteratively introduce actors into the simulation environment with different kinds of incentives and different kinds of capabilities, and then train them against each other in the same environment. And over time, what we'll see is a zoo of diverse actors emerge from this training process, which we can then compose together to create increasingly diverse and complex scenarios. So this is another great way to learn very diverse actor behaviors in closed loop. But one downside of this approach is that it can be challenging to encode human-like driving in reward functions alone. So you really need to be careful about how you design those reward functions. And then last but not least, let's take a look at some ways we can control these actor behaviors. As we discussed earlier, part of what we want to do when we specify scenario is to specify the high-level semantics of how different actors should behave in that scenario. So for example, we might be interested in having an actor cut in aggressively in front of the SDV, or we might want to simulate a traffic jam scenario full of extremely cautious drivers, right? And to do this, we need our actor models to be controllable. So let's take a look at some ways we can do this next. So one way we can do this is to learn goal conditional policies. So here we might want to condition each actor's policy on some driving commands like turn left or turn right, or on waypoint goals specifying where we want the actor to be in the future, or simply as routes along the road network. So these policies allow us to control the what of how actors should behave in a scenario, and conditioning and using this to condition is super simple and interpretable for humans to manipulate. However, these policies often fail to generalize to out of distribution or long tail conditions. And the conditions that we want to control usually needs to be known ahead of time and labeled before we train these models. So besides goals, we'll also want to control the style of the actor. So for example, how aggressive or cautious the actor is. In combination with control over goals that we discussed previously, having control over an actor style would then allow us to create scenarios where an actor would cut in front of the SDV, but with varying levels of aggressiveness, from like very cautious to very aggressive cut-ins. Now, as you can imagine, defining what it means to be aggressive or cautious is really challenging, right? But this really hasn't stopped the community from trying. So we can, there's been a couple ways we can do this. We can define style as sort of the courtesy of an actor, which basically measures how much other actors would need to adjust their behaviors from their nominal behaviors given my choice of actions. So for example, me cutting in front of another actor is not very courteous, right? Because the other actor will have to potentially hard brake in response to what I'm doing. But if I was to just drive beside that other actor, then this behavior is actually quite courteous because the other actor doesn't really need to adjust his behavior at all to account for what I'm doing. Alternatively, we can also define style using something like social value orientation. And this measures how much an actor prefers to allocate its value to itself versus to other actors. So to illustrate what this means, an egoistic actor, for example, might want to optimize his own gain by being quite aggressive, right? And trying to overtake everyone so that it makes a lot of progress. In contrast, an altruistic actor might be one who would yield to these actors because they want to allow others to optimize their progress instead of their own. Other definitions of style include whether an actor is goal or information seeking, whether an actor is goal or safety oriented, or we can also just try to directly discover latent personalities from data using in an unsupervised manner. With these style-based approaches, we can then control how an actor behaves. However, it is quite difficult to define what these styles should be. and the actor model may generalize poorly to novel styles. Cool. Recently, a couple papers have also explored how to control actor behaviors through specifying a reward function for how we'd like them to behave. So using this reward function, we can then use a variety of different techniques to generate the kinds of scenarios we want. So for example, AvSim uses black box optimization to optimize a collision-seeking objective, thus generating adversarial actor behaviors that stress tests the SDV. Likewise, Strive is another paper that uses latent space optimization to find realistic adversarial scenarios in the latent space of a latent variable actor model, like for example, a VAE. Other approaches include sampling from diffusion models using guided sampling, or using reinforcement learning to learn actors that maximize the given reward function. So this approach is really flexible in how we can control actor models, and it's also quite conceptually simple. The reward functions are also composable, and so using this approach, we can actually compose various rewards together into ever more complex reward functions to create ever more complex behaviors. However, because a lot of these approaches require optimization in the loop, inference is typically quite slow. And in addition, while reward functions are quite flexible as a specification tool, shaping those reward functions so that they can be easily optimized is very challenging. So finally, we've seen goals, styles, and reward functions as different ways to control an actor model. However, these different approaches are either not very flexible or expressive to all the different kinds of behaviors we want to simulate, or they're kind of tedious to tune in the case of, say, reward function specification, right? And a much more natural interface to control actor models is natural language instead. And in an age of LLMs, implementing this level of controllability may not be very out of reach. So for example, Diffusion ES and CTG++ uses a large language model to convert natural language description of the kind of behaviors that we want to simulate into a reward function or guidance function that we can then use to optimize, or we can use as a part of guided sampling within a diffusion model. Alternatively, we can also convert natural language descriptions into lower level maneuvers like drive straight or turn right, which can then be executed by a lower level maneuver condition policy. These approaches to controlling an actor model is super flexible and super ergonomic for human scenario authors. However, we're definitely still in the early stages in exploring how we can make use of natural language interfaces to control actor models. A lot of the preliminary experiments done in these papers show how natural language can be used to control very simple behaviors, right? But it's unclear how well this would work as we try to use them for more complex behaviors as well, especially in a closed loop simulation setting. So this is definitely a very exciting space that we should closely monitor going forward. And that concludes our sort of whirlwind tour of actor simulation. So in summary, we've provided sort of a high-level overview of recent work in actor simulation, focusing in particular on diversity, realism, diversity, and controllability. And hopefully this was helpful in giving you an overview of the problem and maybe some of the open questions that remain. And last but not least, I just wanted to take a step back and see how everything fits in back together within the full closed loop simulation system. So earlier in the previous session, Siva covered different ways we can build this asset library from real world data, and how we can simulate sensor data and simulate the vehicle platform and its dynamics as well. In this session, we covered how we can actually generate scenarios that specify the content of the simulation, and how we can actually simulate the behaviors of the actors in those scenarios in closed loop so that we can test and train the self-driving vehicle. So that's it for the simulation session. Happy to take any questions.
In this diagram, actor simulation can also affect sensor simulation. So it will be an error with that course.
Yes, that's a great point. So the way we see this is actor simulation will output controls or how actors' states should change over time. And this would actually affect the world state representation there in the middle. So that world state representation is then what's fed into sensor simulation as sort of ground truth for where the actors are, how they look like, and how you should simulate camera or LiDAR given that. Yeah.
Other questions on Zoom?
Oh, yes. Does scene? Oh, yep. There's one question on Zoom. Does scene control generate actor behaviors and future actions, or just the starting scene? I don't know if you can hear me, but just the starting scene. So scene control only currently only considers the layout of the actors. But there's some other work, related work out there like LCT Gen, which generates both the actor behaviors as well as their initial layouts from natural language alone. One thing to note about those kinds of models, though, is that they generate these actor behaviors in an open loop fashion. So they give you almost like a template of what they expect the scenario to look like over time, right? But then because when they're generating those behaviors, they don't have the SCB executing in the loop. The actors are actually not reactive to what the SCB is doing. So that's why you might still need something like an actor model in the loop so that you can generate behaviors that actually react to the SCB and yeah. Cool.
Oh, there's one more.
Do you have any like intuitions or thoughts on the like this form of simulation compared to the more end-to-end one, the like Wave and Tesla and Comma are all trying?
Yeah. Let me see.
Just like the like world model video generation is.
Yeah.
Repeat the question so it's on.
Yeah. So the question was, do we have any thoughts on how this compares and contrasts against other simulation approaches that leverage world models to directly simulate pixels or sensor data, right? So our approach is definitely a lot more modular than those approaches in the world models. And with this modularity, what that means is we can really control how we want the scenario to play out over time. Yeah, we can really control how we want the scenario to play out over time and really encode our prior knowledge about realistic simulation inside the simulator. So for example, we can use or we can incorporate into our closed loop simulator something like a really realistic vehicle model to simulate how the SCB's actions get translated to its changes in states. Whereas if you were to just use a world model where you condition the conditions you send into it is like accelerate or decelerate, right? Then you don't get that same level of fidelity in your simulations. Additionally, with this approach, because from the scenario perspective, with world models, you really maybe only get high level control over where actors are in the scene. But if you want to be able to really characterize exactly how the SCB would perform over, say, the entire parameter space of a given logical scenario, for example, you would really want precise control of where you place the actors and how exactly those actors behave and respond to the SCB over time. So having this sort of like modular approach allows us to do this. Yeah. Any additional thoughts?
We had a slide earlier in the simulation section that talked a bit more detail about the pros and cons of world models versus the sort of closed loop simulation system. Sorry, I'll stand up. I think like one of the major challenges is that because you implicitly encode the dynamics of the world and the appearance in a single representation, you can sort of hallucinate things that you can't really expect to happen. So the example I gave earlier was that even if you have action conditioning in your world models, if, for example, you have a very dense traffic scene, and then you have your self-driving vehicle for some reason accelerate into this dense traffic scene, currently your world model will just kind of hallucinate and say, oh, this isn't very common in my data distribution. I'm going to make these actors disappear and then just create something more realistic that is very common in my distribution. You can see this like with Sora too. Oftentimes like the scene, as you evolve it over time, it morphs a bit so that it just kind of like, so this looks reasonable. And like on the shorter time scale, it is realistic. But in the longer time scale, you actually can't guarantee the reactive behavior you want with your actors with your self-driving vehicle right now. and it's a bit hard to use that type of model for safety critical testing. I think world models can still be very beneficial for building high quality asset representation and generating like data for like good perception representation learning. But to use it for testing evaluation, where you really want to understand the performance of your system in a very particular scenario and make sure that it's safe, world models are not maybe a good solution for that situation.
Cool. All right. We can continue, let's say, in 15 minutes at 5 minutes past 4 with the remaining sessions, which will look at the kinds of maps and map representations that we use, as well as localization. And then we will end up with additional time for any leftover questions folks might have. Thank you.